My name is Andreas Olofsson, and I'm currently in Boston, but I'm from Sweden originally. It's my second time in Bristol. So, anybody know where I ripped off this title from?
Feynman.
All right, there you go. So I added one word, still. There's still plenty of room at the bottom. Of course, it's from Richard Feynman's famous lecture more than 50 years ago. So the idea was, the challenge he placed was, we're doing great, we're miniaturizing electronics, and yet there's so much more we could do. I don't know if everybody here knows, he actually was involved in supercomputing. He was part of the connection machine work, the network, the very, very sophisticated network they had. He took a sabbatical, I think, one summer, and actually went in and worked on it. And of course, he was an amazing person, as brilliant a genius as he was. He wasn't beyond getting his hands dirty and doing some actual chip design. Very, very inspiring man. Why is this question still relevant? Is that we have an efficiency problem today, as everybody here already knows. I don't need to preach to the choir. But we've had a pretty good ride in 1980s, 1990s. We were getting more performance every year. Energy efficiency was not really a big concern. Today, energy efficiency, of course, is a huge concern. What matters is how many operations per watt you can do, not how much raw performance you can get. And that's absolutely true in embedded, but it's also becoming a real pain point in data centers and supercomputing. So we have to figure out, well, how can we do more with less? Of course, these are some of the fields that we're involved with right now. And these are really people that are coming to us and saying, we have a real energy efficiency problem. Certainly there are fields that only care about performance today. Some HPC applications, it's really about, how many teraflops can I get in my desktop? Power, not really a big concern. It's plugged into the wall. It's 1 kilowatt, 2 kilowatt. We can deal with that. If we're talking about massive scales, about megawatts, power is obviously a concern. If we're talking about battery-operated devices, power is always a concern, and it always has been. So that's why we started this company in 2008. The idea was that we can do better than what existed in 2008. It's taking us quite a long time to get to production, but we've also had to do it with a very small budget, so it's become a serial process, which of course always takes longer. But we started in 2008. We are a X company, right? We've been called many names: coprocessor, accelerator, many-core, multi-core DSP. We'll present what we have. You call us what you want. We've shipped 16-core devices since last year as products. We started sampling a 28-nanometer device this summer. Most recently, we launched a kind of open computing project called Parallella, which the idea was, a processor on its own without an ecosystem is pretty useless. So you need to basically reduce the hurdles, the barriers of entry, to get as many partners as you can, and that's how you become successful. It's been done, many times over. It was done by ARM very, very successfully. It's now been done by NVIDIA very successfully. And this is our way of doing the same. And I'll talk more about that project later. We've done 4 chips so far, a little bit less than $2.5 million. We've already demonstrated 50 gigaflops per watt at the chip level in the lab, proper operations. All our flops, by the way, are single precision floating point, because we really target more at the embedded space than maybe the high-end supercomputers. We can actually put 1,000 CPUs on a chip today, and real CPUs. I mean, real RISC processors. $2 million in revenue, and based on this parallel project, we now have 5,000 customers, and we're less than 5 people in the company, in case anybody was wondering. So this is our vision for the future of computing. There tends to be a lot of jousting between the different potential offerings, right? If you're an FPGA company, well, FPGAs can solve all the world's problems. If you're a GPU company, same thing. CPU, same thing. we really believe honestly that the future is you need everything, right? Efficiency is, the issue. Then you need to put the right tool for the right problem everywhere. And a GPU can't solve all the world's problems. Same thing with FPGAs. Everybody has their blind side. Everybody has their inefficiencies, as do we. And so the right solution is put together a system best in class for every problem. So that's what we want to build. That's what we're trying to build. We really try to focus on making really, really efficient small floating point processor or small accelerator processors. Not trying to write an operating system, because there are really great processors for doing that. You have ARM, you have Intel. You're not trying to do graphics, because GPUs are really good at that. Not trying to be the most flexible I/O solution in the world, because FPGAs are really good at that. So future systems, I don't think we're too far off from this. Companies like Altera and Xilinx are already working on hybrid FPGAs where they have dual-core ARMs and a little bit of FPGA logic. They don't have a GPU in yet. I'm sure it's coming. So now you have most of that picture is already done. It's practical products by big companies. What we're trying to push in is our many-core, many small RISC processors. So this is part of the jousting, what really matters here is efficiency. It's sometimes between all the hype between peak numbers and Moore's law scaling and comparing versions at the same technology node, it's very, very hard to make an apples-to-apples comparison. And so I try to do my best effort to see where the different technologies fit in terms of compute density. And so to do that, you really have to look at millimeters. So, for example, if you have a teraflop chip from, the latest GPU, what does that really mean, right? Compared to an architecture that might have 64 cores and 100 gigaflops, it doesn't seem very impressive. But I think if you look at how much silicon area you take up, you can normalize the two numbers and say, well, if you scale up one technology, scale down the other, what would it look like? And that's kind of like, it's another way of looking at the gigaflops per watt number. But gigaflops per watt only shows floating point performance. What about memory density? What about integer performance? What about number of cores? How do you compare those things? So this is, what this table shows me is that, you really want a heterogeneous solution because none of these technologies is going to solve all problems. And the final thing I wanted to say here is a lot of nonsensical talk about peak performance, which every vendor puts up there. What real users care about is real performance. So if you have a teraflop chip, that's nice, but how much of peak do you get out in your application? And there can be a factor of 10 to 100 away from peak based on the skill of the programmer as well as the complexity of the program. So certain applications don't map very well to certain architectures. So you really have to pick your architecture. So this is what we came up with in 2008. And so the idea was, I used to work at Analog Devices for 10 years on DSPs, processors like the Tiger Shark DSP, and learned many very valuable lessons in that work. We spent about $100 million in developing the Tiger Shark over 8 years, and at the end of the day, it just wasn't economically feasible to go forward like that. The processor was very complicated, VLIW processor, and the floating point unit, which I was in charge of, was about 1% of the silicon area, and that really pissed me off. Right, I was working really hard, and it was 99% overhead as far as I was concerned. Right, the floating point was the star of the show, and so looking at that, basically you make a spreadsheet, make a pie chart, you look at the components. Well, what can we throw out there, right? And so we start looking at things like memory system, right? Caches was a huge area consumer. It was a very, very complicated cache with instruction cache, data cache, prefetching. It even had DRAM on chip, and so that had to go to get the density up. Look at the sequencer. Tiger Shark had 1,000 instructions. That is going to be a lot of decode logic, a lot of muxes. So you need to get that out. You start looking at buses, different I/O. Supporting every I/O standard in the book is going to cost a lot of area and performance. So basically, it was looking at the CPU and making it as small as possible, but not smaller. Right? To rip off another famous quote. But the idea here is very, very small instruction set. So we have about 35 instructions in our CPU. So this is going back to the RISC processor of the early 1980s. So have a very, very small instruction set architecture, and then see what kind of performance you can get out of that. And at least to us, surprisingly enough, we gave up very little. It was the performance was good enough for a modern compiler like GCC. It doesn't need a lot of instructions. What it does want is a lot of registers. So we spent our transistors on a big register file. So we made a very, very small CPU, a very, very simple memory system where we maximize the number of bits of storage per transistor. So like in a cache, for example, you're going to need a lot of overhead for every bit of storage that you have. If you really care of maximizing density, you want to just have SRAM, just a scratch pad, an addressable scratch pad. So that's what we put in. So looking at that instruction set architecture, floating point is a star, maximize the number of transistors on the floating point. Memory, same thing for the bits. And then finally, need to connect all these processors with a network. You can't use a bus anymore. So we designed a network to connect these processors. And the same kind of design philosophy is make it lean, make it small, but not too simple. So it's the network we use is a packet network where every core can talk to every other core, but just an address. So if you run a program, a C program, one core, and you want to talk to another core, you set a pointer, and the network takes care of everything else. That's at the very base level. So that's, these are all independently programmable processors. So it's, it's a MIMD type approach. Looking back again at the Tiger Shark experience, we had some very, very smart programmers that could do magic with that processor, but there were very few of them. It didn't scale very well. So, SIMD, VLIW, complex pipelines, we wanted to make the programming experience as simple as possible, even giving away some performance for that. And I think one of the most interesting things of this work is that, if you make things small enough, you take away the majority of the waste. Between 1% efficiency and 100% efficiency, there's a big range. Well, what if you can get to 30% of peak efficiency with this architecture compared to SIMD? Maybe that's good enough, and you really gained a lot of flexibility in having MIMD versus SIMD. So that's our architecture, and that, of course, kind of fits in here, right? We're not a standalone processor. We always sit next to something else, and that's where we want to fit in. Basically a new socket in the SoC or a new socket on the board. So in terms of programming models, we believe that basically we're agnostic. We can go data parallel, like OpenCL, a SIMD type approach, or we can do task parallelism because every one of our cores is independent. Really, we're not proposing a solution. We're just proposing a fabric that people then can pick and choose. We think message passing for streaming type applications is fantastic. So we're working on supporting that. We already have a rudimentary task-based parallel model in place. We have an OpenCL compiler in place. So going forward, we're really looking forward to seeing what people can innovate with this. So some more revelations that we found out in the last 5 years, and this one came really only this summer. So we started the company thinking, a Tiger Shark and others, business-to-business approach, deliver as close to solution as possible. But of course, with 5 people, we couldn't do the left side model, right? We couldn't create a solution, right? We need partners. Partners are very hard to come by if you don't have a lot of money. You need to pay your partners to do work for you. And then, so this summer, we turned the pyramid over and we said, well, we've always been a platform company trying to be something else. Now we said we're going to be a platform company. We're going to develop communities, and to do that, you need to make it open. So we released all our documentation openly without NDAs, which is, to some people not a big deal, to other people it's a very big deal. You know, there are horizontal chip companies out there who have always released their data sheets. To them, it's not a big deal. To startup companies, that are, you know, you tend to be a little bit paranoid, and for good reason sometimes. And so you don't release the information, but it really hurts you. So we decided release the information. The other thing was, you know, cost. Our kits, we used to sell them for $10,000 because that's what people do, or $5,000. That's going to keep pretty much everybody on a lean budget away from your technology. So you have to reduce the price. And you know, and software tools, everybody wants them for free. And so one company that inspired us here was NVIDIA, right? I mean, they've really brought the barrier down of entry for HPC to a very, very low level, and done a great service in doing that. But at the same time, it means that we have to come down there as well. So that's what I think, you know, and this is what we've learned. But I think there are other trends in the industry that even for handset or other devices that people need to open up their architectures. You know, it's if you're a handset manufacturer, if you can open up your platform and do this kind of thing, you're gonna do a great service to society. So this is the project we launched. We launched it on a US platform called Kickstarter, which is a crowdsourcing platform. And basically the way it works is you put up a project and you say, this is what I want to build. This is how much money I need to raise. And then people put in money, you know, anywhere from $100 to $1,000 to $10,000. And it's a pledge, right? It's a donation, and then you give them a reward in return, which generally needs to be something tangible, right? Otherwise people wouldn't put in the money. And for us, it was, you know, we said, if you put in $100, we'll give you a board with some pretty good specs on them and one of our chips on them. And to produce that at $100 is not trivial. It's very, very challenging for us. So they were getting good value for their donation, but it's not meant to be a store. It's meant to be a kind of a donation and reward process. You know, it gets around liabilities and SEC and all kinds of regulations. But everybody gains. So basically what you do is you go directly to the consumer, directly to the developer, instead of, you know, trying to raise lots of money, build it, and then sell it. So it's kind of an innovative idea, and there have been a lot of great projects launched on Kickstarter. And so we tried this. But this really meant that to have this kind of platform, we needed to completely change our business model. Basically open up everything, make everything free. And the only thing we kind of keep for ourselves is our own proprietary code for the chip. Everything else becomes open. And so far it's been great. It's been fun. It's been fun to meet lots of new people, get a lot of great feedback. And we signed up something like 4,000 developers in less than a month. And for a semiconductor company, this is a breakthrough. You know, if I look at Tiger Shark, we never had 4,000 developers for the Tiger Shark, and we spent $100 million and 8 years working on it. And this just turned it on. Of course, now we have a big responsibility to deliver about 6,000 dev kits to these backers by May. But that's something we cherish, right? Engineering challenges are great. To sell the technology is much harder. So now we've sold it. Now we just have to deliver. So we look forward to that. In terms of you know what this means, right? I think just if you take a step back and look at the history, right? And this is just Moore's law in effect, but I want to point to, you know, how much room there might be left, right? So, you know, not to look back and pat ourselves on the back that said we've done great, but really say we've done great, but we can do even better. So if you look at the connection machine, you know, from 20 years ago, about 100 gigaflops, a lot of money, a lot of power. Today, that machine fits on the parallel board, if you look at the performance. There are other boards out there too, right? There are GPUs talking about 100 gigaflops coming out next year. You know, basically an iPhone or an Android device are going to have those kind of performance levels at a roughly the same price. So this is ballpark figures. But still, this is, to me, this is pretty amazing. And we, yes.
The other aspect is they sold about 200.
200 machines.
Yeah.
Yep.
Total,
yep.
Opposed to hundreds of millions.
Right. In terms of the popularity of them, you mean, or yeah?
No, just in terms of how many units were actually shipped.
Yeah. No, absolutely true. I mean, and this is a very good point. This is part of the parallel project too, right? Is, you want to put parallel processing in the hands of everybody, not in the hands of just the elite, right? And so access to these connection machines was very limited, and that is one of the problems. Again, GPGPUs has done a great service there. They put parallel processing in the hands of a lot of people. And we want to continue that, right? With this kind of project, we want to put parallel processing in the hands of everybody, and open enough that anybody can use it. So that is absolutely the idea. So now getting back to the the Feynman inspiration, smartphones, right? Incredible devices, but if you look at the volume of the actual device, right, with the screen, with the battery, and the radio and everything else, and you go down to the floating point unit. Which, again, sorry I'm being floating point centric, but it's the star of the show. There is an enormous reduction in volume. And just, kind of to always remind ourselves that, if you want to build something much smaller, it's not that hard. It's trivial, right? The silicon die that, 13 millimeters on the side, that's not big. And that's a very, very big die, by the way. Our dies are only about 3 by 3 millimeters. So that you can pretty much put anywhere with the right packaging technology. So really, as amazing those devices are, I want one in my watch, right? And I don't want to change my battery every day. I want to charge once every 5 years. Same thing goes for exascale, and this is more of a kind of a thought. If we look at, there's a lot of efforts in the U.S. on exascale programs, a little bit stop and go sometimes, but we're talking about a lot of money here. Let's say $1 to $10 billion to build an exascale machine. And so if you look at the floating point portion of that, which is a big part of it, just the silicon cost, and this is based on our 65 nanometer chip, the silicon cost for the processors would run about $10 million. So, and that's 65 nanometer technology, which is outdated today. So looking forward, and the density should get better, the cost per transistor should get better, otherwise there'd be no reason to scale. And this is just a thought experiment, right? And obviously there's so many more components in a machine. There's network cards, there's memory, there's disks, and so forth. But it does seem, like there's a 1,000 to 1 ratio in the cost, that there's a lot of room there for maybe re-engineering the system, so that, again, putting the floating point processor at the center, not as a byproduct. So I hope somebody takes a look at that and tries to build a different kind of system. Because right now, if we keep doing what we have been doing, it is going to be $10 billion to build. So capital efficiency, this is absolutely one of my biggest pet peeves in talking to people, in the misinformation that is out there. And the misinformation is partially based on data, which is, as most disinformation is, but it's completely taken out of context. So if you look at big systems on a chip, they can be very, very expensive to develop. But there are very good reasons for that. They're very, very complex projects. You look at Apple's processors. Apple probably spend something like $1 billion on their platform, if you include everything together. The IBM cell with Toshiba and Sony and IBM was about $1 billion to develop, if you look at everything together. Now, those companies, they make money on that. That's not a bad investment. If you look at all the consoles that were sold with IBM cells in them, if you look at all the smartphones sold, that is chump change. Apple puts many designers spend millions of dollars just tweaking GPUs down in Texas, so that they can squeak it, a little bit more battery power out of the processor. That's a great investment. For most people, it's not a good investment. But when you're selling billions of dollars worth of product, and this is the tail that wags the dog, the chip that's a little bit better, that makes sense. But nobody besides IBM and Apple are going to spend $1 billion doing something like that. Most other companies will spend $100 million. These might be the Qualcomms, the TIs, the Marvells, and they can do that because they sell hundreds of millions of devices at $10 to $15 each. $100 million to spend is not a lot. Startup might spend $10 million because they're leaner, right? They don't go overboard with their spending. We spend less than $1 million per chip because we do that even more. We could spend $100,000 with certain tweaks to the model. So next time somebody says an SoC costs $50 million to tape out, just tell them no, not really. Depends, right? It always depends. So if you can do a chip for $100,000, there are a lot of markets that open up, especially if you don't care about the per unit price, right? If you have a market, whether it be scientific or military, where you're only going to order 100 chips, what you can do is you can build a shuttle, and you're going to pay $5,000 to $10,000 per wafer, so your per unit cost is going to be $200 or $100. If you don't care about $100 or $200 unit cost because you're only going to need 100 of them, but you really care about performance, you might want to think about taping out a chip. It's not a big deal. Don't think $10 to $20 million. If you have the right people, you have the right infrastructure, think hundreds of thousands of dollars. And we've shown that. Not every chip. You're not going to build the next application processor with $100,000, but you can build a programmable ASIC for $100,000. So these are trends that I really believe to be true. Some of them tend to be kind of controversial, but they definitely have driven my thinking in what kind of architecture should be built. Power consumption is not really that controversial. It's a big issue, so we need an architecture that's efficient. That means less transistors, less silicon. Very clear. Memory bottleneck. We run into this a lot. The idea is that you have so much density on a chip, but not that much memory. So you're going to have an I/O bottleneck if you don't write your program the right way. And in most of the algorithms that we do, we say, well, what if we can get rid of the DRAM? And so we as much as possible, we try to write algorithms that we don't need DRAM. Because as soon as we do, it's kind of you get this cliff, and it doesn't work as well. And I can talk offline about some examples for that. Frequency wall, not a controversy. We're not going to hit 10 gigahertz anytime soon without carbon nanotubes or something. So parallelism is the only way to get performance. Wiring, and this is a chip-inspired issue from my days at the Tiger Shark. And the idea is that if you have global interconnects, you're going to have to work very, very hard to get over the fact that wires are slow, and they're getting slower. And so what you need to do is you need to have an architecture that's distributed enough that you guarantee to have only short interconnects. So if you build an architecture that has very, very small tiles and you only have nearest neighbor communication, you don't have a wiring problem. You never will have a wiring problem. It doesn't matter if you're at 14 nanometer or 6 nanometer, you're fine. If you have long interconnects, your architecture is not going to scale very well. So you don't want global wires. And for architectures, this means that, for example, very, very wide SIMD architectures are going to have to solve that in a clever way, because they, by definition, have global interconnects. But there are ways around it, but just you have to work harder at solving that problem. But distributed architectures is the answer. Thermal density. At 28 today, we have a big thermal density problem even on our chip, because we put our 64 cores on a 3 by 3 millimeter area and it's burning 2 watts. Sucking 2 watts of power out of a 3 by 3 millimeter area is not trivial. You need a very good package for that. And I can only imagine once we go down to 14 nanometer, now it's going to be 2 watts out of a 1 by 1 millimeter area. It's only going to get worse. And so everybody has this problem. But it's worse if your architecture isn't balanced. So let's say you put all the floating point units, all the hot units on one side of the chip, all the cache on the other side of the chip, you're going to have a thermal gradient across the chip that's going to be pretty ugly, and that's going to make your problem worse. And it may mean that you can't run as close to the edge as you could if you had an architecture that was homogeneous, right, across the chip. So a better, less of a thermal gradient. Latency wall, bandwidth is not always the answer, right? Even if you could have optical interconnects onto the chip with massive bandwidth, you might have a latency problem, and that comes back to software. Yield issues, I don't know if you've seen in the press, but there were lots of people who had 28 nanometer yield issues. It's a big deal. And in the past, we put a lot of burden on the foundries. Basically, foundries, please make us a perfect process. And here are the design rules. We'll throw it over the wall to you guys. You produce it and give us 90% yields, please. Today, there seems to be a lot of design-dependent yield issues. So some companies are not complaining about yields. Other ones are. Well, probably it's because their design was not designed the right way for 28 nanometer. So going forward, you're going to see a lot more uneven distribution between different products. So if you design your product well, you're going to be very, very profitable, have 60s, 70s, 80s, 90s yields, no problem. If you design your product with yield issues, you might see 10% yield. It's very hard to make money as a chip company if you have 10% yield. And so now here's where the architecture can help, in that if you have an architecture that has natural redundancy, you don't have a yield bottleneck, you can get around that problem kind of elegantly. So for example, multi-core, people have done this for a while. IBM Cell did it with 8 and 10 processors. Tylera has done it. GPUs, I'm sure, do it. FPGAs do it. And the idea is that if you have a fabric that is multi-core from the start, you can make different devices. You sell a device with 100 cores, that's your super-duper 100-core device. And then you sell a bottom-of-the-barrel device with 90 cores, right? And you sell that for a lower price. And if somebody only needs 90 cores and he's willing, he wants to pay less money, he gained. And the company gains in that now they can reach almost 100% yield. Time to market, today, 28 nanometer takes a very, very long time to produce, even with a chip. So we talked about a $100,000 project cost, but it's going to take a long time for you to get your chip. So you don't want to spend too many of those ASICs if you care about time to market. And that's where programmability comes into play. So you basically, I think everybody says that today, whether, of those companies, FPGA, CPU, GPU, everybody says programmability. Software complexity, it's an issue. If we talked to a lot of mobile processor companies about licensing our technology, and I can say that number one concern at pretty much every place was software complexity. The brute force method of solving everything with more manpower doesn't always scale very well. So sometimes you want an architecture that is easier to use. And Amdahl's law is always going to be with us. If you have a serial bottleneck in your program, you're never really going to see a 100x speed up or 1,000x. So those are kind of the trends that I think are going to drive the future technology for computing. So now, if we execute on that, the future I think looks pretty bright for parallel processing. We can do 1,000 cores today. This is just 28 nanometer technology, nothing special about it. And there's a couple of cool things about this. One is you can turn on cores on a per core basis, so it's a very, very granular power consumption. So if you do power gating on this kind of scale, you can actually have a 1,000 core chip with a standby power of 0.2 watts. And then you can ramp it up to 20 watts when you really need the power. And so that kind of peak. So sometimes you have very, very high peak demands, right? And you might go up to 20 watts. So you design your thermal solution for 20 watts, but in terms of battery life, the average might be closer to 1 watt. So that kind of burstiness is, which we see now in a lot of applications, is very powerful. And if you don't have the small scale granularity, you're not going to be able to have that kind of scaling. So 10 years looking ahead, what do we have? By the way, one of the biggest challenges we've had so far with the programming model is we had to limit the amount of memory per core. So we had 32 kilobytes of memory per core. And it's, which is great for kernels. right? But if you're writing a C program, you know that 32 kilobytes is not a lot for code, especially compared to what people are used to in today's CPUs. Yes?
That was code rather than data?
Code and data. Yeah, sure. But, 3D scaling is coming. We've heard that for a while, but I believe that where there is a will, there's a way. The reason that there hasn't been 3D scaling yet is because there hasn't been an acute need for it. There's not a fundamental problem there that can't be solved. And so let's say we build a chip. We get through Silicon VS to work reliably. We stack 10 memory chips on top of each other through Silicon VS. And people are looking at that today with a hypermemory cube, for example, with DRAM. So that is going to drive the technology forward very well in terms of knowledge of how to manufacture. Let's take that technology and map it with a many-core processor. You put the many-core processor on top because it's hot, and you need good heat dissipation. You put all the memory there. Now you can imagine having about 1 megabyte of memory per core. Now, 1 megabyte should be enough to do some interesting problems. And when you look at the 1 megabyte per core times 16K CPUs, that's 16 gigabytes of memory together with a processor. And it's all local. There's no I/O problem, right? With the 3D mapping, you've solved part of the I/O problem. So I think that's pretty exciting. And somebody will build this. I don't know if it's us or somebody else, but somebody should build this, I should say. So that's where we're going. That's our 10-year roadmap if we survive that long. So in conclusion, what I believe is the future of computing is open. No NDAs, low cost of entry. It's heterogeneous. No processor is going to solve all the world's problems. You need to basically pick the right tool for the right problem. I personally believe in task parallelism. If I look at the history of programmers, task parallelism has been used very, very effectively by a large amount of people. SIMD-type parallelism has been used very effectively by a small group of people. But going forward, everybody needs to become a parallel programmer, and I think task parallelism is the answer for that. And computing needs to be efficient. No more hiding in Moore's law. The most efficient architecture will win 5 years forward. And so, grand challenges. And this will happen. The question is when. Will it happen 2 years from now or 10 years from now? But it seems pretty obvious that something has to change fundamentally. So we have to change the way we build our computers after having done a certain way for 50 years. We have to rewrite billions of lines of code if we want more performance. And we have to retrain millions of programmers and rewrite our whole programming curriculum. So, no big deal there, right? So I think it's very exciting. I absolutely I love my work, and I think going forward we're going to see a lot of changes, which is good.
Thank you very much.
All right.
We have 2 microphones. There's another microphone at the back somewhere. So if anyone would like to ask a question, please put your hand up, and we'll get a microphone to you. Hopefully that's working. We can see an on button. I think it's on. Oh, there you go. Just need to be a bit closer. So does anyone have a question for Andreas? We have some at the front, and we have one over that side as well. Here you go.
Bill Langdon, UCL. Would like to take issue with your second point, rewrite billions of lines of code. The assumption there is that people are going to do that, or are you going to get machines to do that?
So I'm full disclosure, I'm a chip designer. I have 1 course in programming in my career, and that was my freshman year of college. So these are, you guys know a lot more about programming than I do, but it seems that at least from a chip design standpoint, that there hasn't been an auto-parallelizing compiler yet written. And so until somebody writes that, I mean, there are things like OpenMP, OpenCL, MPI, and if you look at a single-threaded program, there might be tools out there to help you, the programmers, migrate to parallel code. but I haven't seen something automatic.
Will you see something automatic? So there's a driver for it.
Again, that's just my opinion. It's probably a very hard problem to solve if nobody's solved it yet, because there have been parallel architectures out for forever. I mean, the transputer, the connection machine, and so forth, and a lot of research done in it, but nobody's solved the problem yet of making it automatic.
So several of the other talks later this afternoon, I think, will be addressing exactly that kind of question. So we'll keep coming back to that, I think. Great question. There was one on this side.
Jeremy Bennett from Embercosm. Andreas, one of the things that comes from Kickstarter, of course, it generated a huge amount of interest in communities that you don't normally associate with this sort of stuff, which is precisely what you were trying to achieve. Given this is the UK Many-Core Conference, it'd be interesting to know how that sort of panned out around the world, where you got the interest from, what sort of communities, what sort of geographies.
So we still have to put together the final statistics, and we'll publish that. But we know that we have more than 2,000 international backers all across the globe. A lot in the UK, but pretty much everywhere. You know, we had a lot of backers from Japan, from Australia, from Russia, from Sweden, from Israel, and as well as a lot of backers from the US. So I think there's a global demand for a cheap parallel processor.
More questions?
So is your Kickstarter still open, or is there some way that we can gain access to your dev kits if it isn't?
So yeah, we're working on that. The problem is the pricing, right? So we set a $100 price for the Kickstarter project because we felt that was the magical price point, but it's very hard to reach a $100 price point. It's not trivial. And so until we lock it down and know for sure we can produce at $100, we don't want to open up our exposure more. So we're going to get there. It just, it's a few more weeks. And then we'll open up to everybody.
Yeah, hi, it's Ray McConnell from Blue Wireless Technology. Just a couple of questions on scalability. Your previous slide showed a 16K CPUs. Does that really scale? I mean, certainly a processor in the middle of that, in that die area, is going to be constrained by the amount of I/O bandwidth to the external world, and of course, as the grid grows, it'll get less and less bandwidth to the outside world. Is that true?
So I mean, this is my 10-year plan. So obviously, I'm glossing over some details here, but there are some things that I think are going to help. I mean, mesh networks are very well understood. They've been around for a very long time, and so there are theoretical papers that can show what the problems are as you grow. But you can build more complicated networks that aren't true mesh. There's some kind of hybrid to improve the bandwidth in the middle. That's one thing. The other thing is, if you do have 1 megabyte of memory per core, it also makes the problem slightly better.
What about reductions? At some point, there's a potential problem where all these processors have to collectively produce an answer, and surely the more processors you have, the longer it'll take for that reduction to take place?
Yeah, well, I mean, again, this is not a SIMD architecture, right? So depends on what kind of reduction problem we're talking about. But it's if you take something for example, a very, very large scale 2D FFT or 3D FFT, what you can do is basically load in the image to the array, the whole image, right, and crunch on it for a very long time. Something like that, where you have basically really, really maximize your locality so that the memory is always on chip. Now, true, you have to shuffle a lot of data around, but the network on chip is really, really fast and really, really efficient. And then as soon as you go off chip, you have an enormous bottleneck. So the idea here is load the whole data set onto the chip, or at least a big enough chunk of the whole data set that you can work on it for a very, very long time.
So I think we've got time for one more question, and I'll give Mike the chance.
Hi, Mike Giles, Oxford. Looking to this future, how do you see the energy budget being split between the processor, the memory, and the networking?
So on the chip level or on the system level?
Well, the networking both within the chip and between chips. I'm not sure which of those is.
So today, we at the 28 nanometer, it's about 1.5 watt for core power and 0.5 watt for I/O power. And the I/O is the off-chip I/O, right? And we use LVDS for off-chip signaling right now. So it's possible to think of something that's more efficient than LVDS, but LVDS to us is pretty efficient. So then you're talking about 25%, 75% split between processing and I/O. As we make larger arrays, if we have less I/O, that's going to become maybe 90-10. Now within the chip itself, within the processor array, the majority of the power we want to be in the floating point unit, right? And in network is, if we look at the area breakdown, it's about 50% area for memory, 50% for logic in our processor array. But the memory itself is fairly power efficient because most of those transistors don't move. The network itself is less than 10% of that of each tile, each processor tile. So, yeah, I mean, our goal is to drive it so that floating point unit is the centerpiece, or the arithmetic unit.
But as you ramp up the amount of memory per core, then that's also ramping up the power consumption there.
Absolutely, and that's why we have here the 32 kilobytes per core. Well, one thing about the 1 megabyte is you're not accessing all the banks at the same time, right? It's not like 1 megabyte is 64 times more than 32 kilobytes, or 32 times more than 32 kilobytes. So, you're going to see more power, but not linearly so in terms of memory.
Great. Well, I think that's all we have time for. So let's thank our speaker again. Thank you, Andreas.